Right now, every galaxy in the universe is racing away from us at speeds that would make your head spin. The farther away they are, the faster they flee. Some moving at over 600,000 miles per hour. But here's where it gets weird. They're not actually moving through space at all. Space itself is stretching, carrying everything with it, like dots on an inflating balloon. We'll journey through the discovery that shattered our understanding of reality. Explore why asking what the universe expands into makes no sense, and discover how space itself can grow without needing anywhere to grow into. We'll visit the cosmic microwave background, witness dark energy tearing the fabric of existence apart, and confront the possibility that our universe has no edge, no outside, and no end. Don't forget to like and subscribe for more mind-bending cosmic journeys. Prepare yourselves, we begin. In 1929, a quiet astronomer named Edwin Hubble pointed his telescope at distant galaxies and discovered something that would shatter our understanding of reality forever. Hubble noticed that nearly every galaxy he observed was moving away from us. But this wasn't random movement. The pattern was perfect, almost mathematical in its precision. Galaxies twice as far away were moving twice as fast. Galaxies 3 times farther were racing away 3 times faster. It was as if the entire universe was participating in some cosmic choreography we had never noticed before. Think of it like standing in the middle of a crowd where everyone starts walking away from you at the same time. Except in this cosmic crowd, the people farther from you aren't just walking, they're sprinting. And the people at the very edges are running so fast, they're practically flying. Hubble measured this using something called redshift. When light travels from a moving source, it stretches or compresses like sound from a passing ambulance. Light from galaxies moving away from us gets stretched into longer, redder wavelengths. The faster they move, the redder they appear. Some galaxies were so redshifted that their light had been stretched to nearly twice its original wavelength. This discovery revealed that space itself was growing. Every cubic inch of empty space was slowly expanding, pushing galaxies apart like raisins and rising bread dough. The universe wasn't static and eternal as everyone had believed. It was dynamic, growing, evolving with each passing second. But Hubble's discovery raised a question that would haunt physicists for decades. If the universe is expanding, what is it expanding into? The answer would challenge everything we thought we knew about space, time, and reality itself. What we discovered next would make Hubble's revelations seem simple by comparison. The word expanding tricks our brains into imagining the universe like a balloon growing bigger inside a room. This comparison feels natural because every expansion we experience in daily life happens within something larger. A balloon expands into the air around it. A city expands into the surrounding countryside. Even an explosion expands into the space that was already there. Our minds automatically search for the room that contains our expanding universe. But cosmic expansion works completely differently. The universe isn't growing into pre-existing space because there is no pre-existing space. Space itself is what's expanding. It's like imagining a balloon that creates new room around itself as it inflates. without any walls or boundaries to push against. Picture a piece of graph paper with dots marked on it. Now imagine the paper itself stretching so that every square becomes larger. The dots move apart, but they're not traveling across the paper. The paper is carrying them apart by growing beneath them. This is closer to what happens in our expanding universe. The stretching happens everywhere it wants, between Earth and the Moon. Space expands by about 1.5 inches every year. Between our solar system and the nearest star, space grows by thousands of miles annually. Between distant galaxies, space expands fast enough to carry them apart at incredible speeds. Here's the mind-bending part. This expansion has no center and no edge. Every point in space sees every other point moving away from it. An alien on a galaxy, billions of light years away, would see us racing away from them, at the same speed we see them racing away from us. The expansion looks identical from every vantage point in the universe. Scientists call this the cosmological principle. No matter where you are in the universe, the view looks roughly the same. You're not at the center of expansion because there is no center. You're not near the edge because there is no edge. But if space itself is expanding and there's no edge or center, then what lies beyond the boundaries of everything we can see? The balloon analogy that everyone uses to explain cosmic expansion actually makes the mystery worse, not better. When teachers inflate a balloon to show how galaxies move apart, they're accidentally reinforcing the wrong idea. Students see the balloon expanding into the classroom air and think, aha, so the universe must be expanding into some kind of cosmic air too. But this misses the most important point. The balloon example only works if you ignore everything outside the balloon's surface. Imagine you're an ant living on that balloon. Your entire world is the rubber surface. You can move north, south, east, or west across the surface, but you can't move up or down into the air around the balloon. Those directions simply don't exist in your two-dimensional world. As the balloon inflates, your world gets bigger, but there's no outside for you to worry about. Now take this idea and add one more dimension. We live in a three-dimensional space that might be expanding just like the ant's two-dimensional surface. Just as the ant can't step off the balloon into the surrounding air, we can't step out of our three-dimensional universe into some fourth spatial dimension. The key insight is that expansion doesn't require an outside. The balloon's surface can grow without needing to expand into anything from the ant's perspective. The surface simply contains more area than it did before. Similarly, our universe can contain more space than it did before, without requiring anywhere for that space to come from. This creates a profound shift in thinking. Instead of asking, what is the universe expanding into? We should ask, how is space itself changing? The universe isn't moving through some larger container. It is the container, and the container is growing. But this raises an even deeper question. If space itself is expanding, what does that mean for the nature of space and time? Space isn't empty nothingness waiting to be filled. It's a physical thing with properties, and those properties are changing. Most people think of space as the stage where physics happens, planets orbit, light travels, and forces act across this invisible backdrop we call space. But Einstein showed us that space is more like an actor in the cosmic drama. It bends around massive objects. It vibrates when disturbed, and yes, it expands as time passes. Think of space like a fabric that can stretch. When you pull on a piece of elastic, you're not adding new material. You're spreading the existing material over a larger area. The fabric becomes thinner and less dense, but it covers more territory. Space expansion works similarly, except instead of becoming thinner, space maintains its properties while simply providing more room. Here's where it gets strange. New space is constantly being created. Every second, about 1 cubic foot of new space appears between Earth and the Moon. Every year, roughly 15 billion cubic miles of new space materializes between our galaxy and the next closest galaxy. This isn't empty space moving in from somewhere else. It's genuinely new space coming into existence. This creation happens at a rate that depends on distance. Close objects barely notice the expansion because gravity and other forces easily overcome it. Your body isn't expanding. Your house isn't expanding. Even Earth's orbit isn't expanding. But at cosmic scales, where distances are measured in millions of light years, expansion becomes the dominant force. The expansion rate tells us something remarkable. Space is being created at about 70 kilometers per second per megaparsecond. That means for every 3.25 million light years of distance, space expands fast enough to carry objects apart at 70 kilometers per second. Double the distance, double the speed. But if space is a physical thing that can expand, then what exactly is doing the expanding? The afterglow of creation itself still fills every corner of the universe, and it's getting stretched by expansion right now. About 380,000 years after the Big Bang, the universe cooled enough for the first atoms to form. Before this moment, space was filled with a hot, glowing plasma that blocked light from traveling very far. But when atoms finally formed, light could suddenly travel freely across the entire universe. This first light, the cosmic microwave background, is still traveling through space today. Imagine a camera flash going off in a room filled with thick fog. The light scatters and bounces around, unable to reach your eyes clearly. But if the fog suddenly clears, you'd see that flash illuminating everything at once. The cosmic microwave background is like that clearing moment, frozen in time and stretched by billions of years of expansion. When this ancient light first started traveling, it was hot and bright, glowing at about 3,000 degrees. But as space expanded, the light waves got stretched along with it. Light that started out as a visible orange and red got stretched into infrared, then into microwaves, then into radio waves. Today, that same light has a temperature of just 2 7/10 degrees above absolute zero. We can detect this ancient light coming from every direction in the sky. It's remarkably uniform, varying by only about 1 part in 100 zeros and from one direction to another. This uniformity tells us that the early universe was incredibly smooth, and that expansion has been happening in all directions equally. The cosmic microwave background gives us a baby picture of the universe when it was only 380 zeros years old. But more importantly, it shows us expansion in action. Every microwave photon we detect today was once a much shorter wavelength that got stretched by 13 and 8 billion years of cosmic expansion. But measuring this ancient light revealed something nobody expected about how fast expansion is happening. The universe is expanding at different rates depending on where you look, and this contradiction is driving physicists to the edge of madness. When we measure the expansion rate using nearby galaxies, we get one answer. When we measure it using the cosmic microwave background, we get a different answer. These two measurements should match perfectly, but they don't. It's like using two different rulers to measure the same table and getting different lengths. Using nearby galaxies, astronomers measure the expansion rate at about 73 kilometers per second per megaparsec. This means that for every 3.25 million light years of distance, space expands fast enough to carry objects apart at 73 kilometers per second. But using the cosmic microwave background, physicists calculate the expansion rate at about 67 kilometers per second per megaparsec. 6 kilometers per second might not sound like much, but in cosmology, this difference is huge. It's like discovering that your car's speedometer and GPS disagree about how fast you're traveling. Either one of your instruments is broken or something fundamental about the road itself is changing. This discrepancy has a name, the Hubble tension. It suggests that either our understanding of the early universe is wrong, our measurements of nearby galaxies are wrong, or something about the expansion process itself has changed over time. Some physicists think dark energy is evolving. Others believe there are unknown particles or forces affecting expansion. The tension gets worse as measurements become more precise. Instead of converging on a single answer, the two methods are becoming more confident in their different results. It's as if the universe is telling us two different stories about its own expansion, and we can't figure out which one is true. This mystery points to something profound. The expansion of space might not be as simple as we thought. Every search for the edge of the universe leads to the same maddening conclusion. There isn't one. Humans are wired to think in terms of boundaries. Every room has walls. Every country has borders. Every lake has shores. We instinctively assume that the universe must have an edge somewhere, a cosmic boundary where space simply stops and something else begins. But decades of searching have revealed that this edge doesn't exist. Consider what an edge would actually look like. Imagine traveling in a straight line through space for billions of years, passing countless galaxies and stars. Eventually, you'd expect to reach a place where galaxies become scarce, then rare, then disappear entirely. Beyond that, you'd find empty space. And beyond that, what? A wall, a void, a sign that says universe ends here. The problem is that observations show the universe looks roughly the same in every direction, no matter how far we look. Galaxies are distributed evenly across space, out to the very limits of our vision. There's no thinning out, no approaching boundary, no hint that we're near any kind of edge. This doesn't mean the universe is infinite, although it might be. It could be finite, but unbounded, like the surface of a sphere. An ant walking on a basketball would never find an edge. Even though the surface has a finite area, the ant could walk forever in a straight line and never reach a boundary or retrace its steps. Similarly, our three-dimensional universe might curve back on itself in ways we can't visualize. You could travel in a straight line for billions of years and eventually return to your starting point without ever encountering an edge. The universe would be finite in size, but have no boundaries. But if there's no edge to find, then what defines the limits of everything that exists? The universe can be both finite and unlimited at the same time, breaking every rule of logic we learned in school. This paradox becomes clear when you think about the difference between infinite and unbounded. An infinite universe goes on forever in all directions, containing endless amounts of space and matter. An unbounded universe has no edges or boundaries, but it might still have a finite size. These are completely different concepts that our brains tend to mush together. Picture yourself on the surface of Earth. You can walk in any direction for as long as you want, and you'll never hit a wall or fall off an edge. The Earth's surface is unbounded, but it's not infinite. It has a definite, measurable area. You could theoretically walk around the entire planet and return to your starting point. Now imagine this same principle applied to the entire three-dimensional universe. Space could curve back on itself in ways that are impossible to visualize, but mathematically consistent. Just as Earth's surface is a two-dimensional space, curved through a third dimension, our three-dimensional universe might be curved through a fourth spatial dimension we can't perceive. In such a universe, traveling in a straight line would eventually bring you back to where you started. The universe would contain a finite amount of space and matter, but it would have no boundaries. There would be no edge to reach, no outside to expand into, and no center to locate. This concept challenges our deepest intuitions about space and reality. We expect boundaries because we live in a world of walls and fences. But at the cosmic scale, these familiar concepts break down. The universe operates by rules that seem impossible until you realize our everyday experience is just a tiny slice of a much stranger reality. But this raises the ultimate question. If the universe has no outside, what does outside even mean? The word outside loses all meaning when applied to the totality of everything that exists. We use outside to describe the relationship between things within our universe. You can go outside your house into the yard, outside your yard, into the street, outside your city, into the countryside. But all of these outsides are still inside the universe. They're just larger containers within the ultimate container of space and time. When we ask what the universe is expanding into, we're trying to apply this inside-outside relationship to the universe itself. But the universe isn't a thing within a larger space. It is space. It's not expanding into something else, because there is no something else. The universe is the complete set of everything that exists, and you can't have an outside to everything. Think of it like asking what's north of the North Pole. The question seems reasonable until you realize that north only has meaning within the context of Earth's geography. Once you reach the North Pole, there is no farther north to go. The concept breaks down. Similarly, outside only has meaning within the context of space, but space itself defines the boundary of meaningful questions. This creates what philosophers call a category error. We're trying to apply concepts that work within the universe to the universe as a whole. It's like asking what color the number 7 is, or what the universe weighs. These questions sound meaningful, but dissolve when you examine them closely. The expansion of space doesn't require an outside, because expansion is a property of space itself, not a relationship between space and something else. Space can contain more volume than it did before, without needing to displace anything or move into any pre-existing territory. But if there's no outside to expand into, then how do we make sense of the expansion process itself? The expansion of space affects cosmic distances, while leaving everyday distances completely unchanged. Right now, as you read these words, the space between distant galaxies is growing at incredible rates. But the space between the words on this page isn't expanding at all. The space between atoms in your body isn't expanding. Even the space between Earth and the Moon barely changes. Expansion only dominates at the largest scales, where distances are measured in millions of light years. This happens because expansion must compete with other forces. Gravity holds atoms together. Electromagnetic forces bind molecules, and even at larger scales, gravity keeps solar systems and galaxies intact. Expansion only wins this competition when objects are so far apart that gravity becomes negligible. Imagine trying to stretch a rubber sheet that has coins glued to it. The sheet stretches easily in the spaces between coins, but the coins themselves don't get larger. The glue holding each coin together is stronger than the stretching force. Similarly, the forces holding matter together are stronger than expansion at small scales. This creates a cosmic hierarchy of scales. At the scale of atoms, expansion is irrelevant. At the scale of solar systems, expansion is detectable but weak. At the scale of galaxy clusters, expansion becomes noticeable. At the scale of galaxy superclusters, expansion dominates everything else. The boundary between these scales is constantly shifting as the universe expands and matter spreads out. Gravity weakens, and expansion affects larger and larger structures. Galaxy clusters that are barely held together today will eventually be torn apart by expansion. The universe is gradually becoming more and more dominated by expansion as time passes. This process has profound implications for the future of everything in the universe. Dark energy is tearing the fabric of space apart faster every day, and we have no idea what it is. In the late 1990s, astronomers expected to find that the expansion of the universe was slowing down. After all, gravity should be pulling everything back together, fighting against expansion like a ball thrown upward fighting against Earth's gravity. But when they measured distant supernovae, they discovered something shocking. Expansion is speeding up. Something is actively pushing space apart, overpowering gravity on cosmic scales. This mysterious force makes up about 68% of all energy in the universe, yet we can't see it, touch it, or directly detect it. We only know it exists because of its effects on expansion. Scientists call it dark energy, but that's just a name for our ignorance. Dark energy doesn't clump together like matter does. It's spread uniformly throughout space, maintaining the same density even as space expands. This means that as the universe grows, the total amount of dark energy increases. It's as if empty space itself has an inherent energy that drives expansion. Think of dark energy like a spring that gets stronger as it stretches. The more space expands, the more dark energy there is, and the faster expansion happens. This creates a runaway process where expansion feeds on itself, accelerating faster and faster over time. The acceleration is subtle on human time scales, but profound over cosmic time. Galaxies that are currently moving away from us at 10% the speed of light will eventually be moving away at 50% the speed of light, the 90% approaching the speed of light itself. The universe is rushing toward a future where distant galaxies disappear beyond the horizon of observation. This acceleration is reshaping the entire cosmos in ways we're only beginning to understand. The observable universe is just a tiny bubble around us, beyond which lies an infinite ocean of space we can never see. Light travels at a finite speed, so we can only see objects whose light has had time to reach us since the Big Bang. This creates a spherical boundary around us called the observable universe. It's about 46 billion light years in radius, containing everything we can possibly observe. But the actual universe is almost certainly much larger than this observable bubble. Think of standing in a vast ocean at night with a flashlight. The light illuminates a circle around you, but the ocean extends far beyond what you can see. Similarly, our observable universe is just the region around us that light has had time to illuminate. Beyond the observable universe lies more space, more galaxies, more stars, all following the same laws of physics, but forever hidden from our view. These regions are expanding away from us faster than light can travel, creating a cosmic horizon we can never cross. It's like trying to swim to a distant island while the ocean current carries you backward faster than you can swim forward. This means that the universe we study is just a sample of a much larger reality. We're like scientists trying to understand the ocean by studying a single drop of water. The drop tells us about the ocean's composition, but it can't reveal the ocean's full size or shape. The expansion of space is constantly pushing more regions beyond our observable horizon. Galaxies at the edge of our vision are fading away, disappearing as space carries them faster than light can travel. The observable universe is actually shrinking in terms of the number of galaxies we can see. But this raises a profound question about the nature of space itself. Every photon of light traveling through expanding space gets stretched like taffy, revealing the history of cosmic expansion. When light travels across vast distances, it becomes a time machine that carries information about the expansion rate throughout cosmic history. Light from nearby galaxies shows us how space was expanding recently. Light from distant galaxies shows us how space was expanding billions of years ago. By comparing these measurements, we can track how expansion has changed over time. As light travels through expanding space, its wavelength gets stretched proportionally to the expansion. Light that started as blue becomes green, then yellow, then red, then infrared, then radio waves. The amount of stretching tells us exactly how much space has expanded since the light began its journey. This stretching affects more than just color. It affects the energy of light, the rate at which we receive it, and even the apparent brightness of distant objects. A supernova that explodes in a distant galaxy appears dimmer, not just because it's far away, but because expansion has stretched its light to lower energies and spread its photons over a longer time period. The stretching is cumulative. Light that travels for 10 billion years gets stretched by 10 billion years of expansion. Light that travels for 12 billion years gets stretched by 12 billion years of expansion. This creates a cosmic timeline written in the wavelengths of light reaching us from different distances. By studying this timeline, astronomers have reconstructed the entire history of cosmic expansion. They've discovered that expansion was decelerating for the first several billion years after the Big Bang, then began accelerating about 5 billion years ago when dark energy became dominant. But this history reveals something troubling about the ultimate fate of expansion. The accelerating expansion of space is pushing the universe toward a cold, dark, and empty future. As dark energy drives expansion faster and faster, the universe is entering a phase that will reshape everything we know about cosmic evolution. Galaxies that are currently visible will disappear beyond the horizon of observation. Stars will burn out without new material to replace them. The universe will become increasingly cold, dark, and empty. This process is already underway. The rate of star formation in the universe peaked about 10 billion years ago and has been declining ever since. As expansion separates galaxies, they can no longer merge and trigger new bursts of star formation. The universe is slowly running out of the raw materials needed to create new stars. In about 1 trillion years, the last stars will burn out. The universe will contain only brown dwarfs, white dwarfs, neutron stars, and black holes. These remnants will orbit each other in ever-widening spirals as expansion carries them apart. Eventually, even these bound systems will be torn apart by the relentless growth of space. The ultimate fate depends on the nature of dark energy. If dark energy maintains its current properties, expansion will continue forever, creating a universe that becomes exponentially larger and emptier with each passing moment. If dark energy changes, the universe might face different fates, perhaps even a reversal of expansion that brings everything crashing back together. But regardless of the ultimate fate, the expansion of space is already transforming the universe in irreversible ways. We're living during a brief cosmic moment when galaxies are visible, stars are forming, and the universe is rich with structure and complexity. This transformation forces us to confront the deepest questions about existence itself. The expansion of space challenges our most fundamental assumptions about the nature of existence, time, and reality. Everything we know about cause and effect depends on the idea that events happen within a stable framework of space and time. But if space itself is expanding, then this framework is constantly changing. The stage on which all cosmic drama unfolds is itself an actor in the performance, growing and evolving with each passing moment. This creates paradoxes that strain our understanding. If space is expanding, then the distance between any 2 points is constantly increasing. But distance is supposed to be a fixed relationship between objects. If space is being created, then the total amount of space in the universe is increasing. But where does this new space come from? These questions reveal the limitations of thinking about space as a container. We're used to thinking of space as the box that holds everything. But expansion shows us that space is more like a living, growing entity. It has properties, it can change, and it participates in the cosmic evolution it contains. The expansion of space also challenges our intuitions about infinity. If the universe is infinite, then it contains infinite amounts of matter and energy. But if it's expanding, then it will contain even more infinite amounts of matter and energy in the future. This suggests that there are different sizes of infinity, and that infinity itself can grow. Perhaps most disturbing is the realization that expansion makes the universe fundamentally uncertain. We can never know how large the universe really is, what lies beyond our observable horizon, or whether our local region is representative of the whole. The expansion of space has made the universe not just physically larger, but epistemologically unknowable. These philosophical implications point to even deeper mysteries about the nature of reality itself. If the universe is expanding, then rewinding time leads to a moment when all of space was compressed into a single point. This logical consequence of expansion is what we call the Big Bang. If space is growing now, then it was smaller in the past. Keep rewinding, and you reach a moment when all the space in the universe was compressed into a region smaller than an atom. This wasn't an explosion in space. It was the explosive beginning of space itself. The Big Bang wasn't an event that happened at a particular location. It happened everywhere at once, because everywhere was the same place. Every cubic inch of space in the universe today was once compressed together in that initial moment. The expansion we observe now is the continuation of that primordial expansion. This creates a profound mystery about the origin of everything. What existed before the Big Bang? The question might be meaningless because before requires time, and time began with the Big Bang. It's like asking what's north of the North Pole. The question assumes a framework that doesn't exist. Some theories suggest that the Big Bang was preceded by a period of cosmic inflation, where space expanded faster than light for a brief instant. This inflation could have been triggered by quantum fluctuations in a pre-existing space-time, but that just pushes the mystery back another step. What created the conditions for inflation? Other theories propose that the Big Bang was one of many such events, perhaps in a multiverse, where new universes are constantly being born. But even these theories must grapple with the ultimate question: why does anything exist at all? The expansion of space forces us to confront the deepest mystery of existence, the origin of everything. Multiple universe theories suggest that our expanding universe might be just one bubble in an infinite ocean of space-time. If our universe began with a Big Bang, then perhaps other Big Bangs have created other universes. These universes might have different laws of physics, different values for fundamental constants, and different rates of expansion. Our universe would be like one bubble in an infinite pot of boiling water, with new bubbles constantly forming and growing. This multiverse hypothesis solves some puzzles about cosmic expansion. It explains why the expansion rate seems fine, tuned for the formation of stars and galaxies. If there are infinite universes with different expansion rates, then some will have conditions suitable for complexity and life. We naturally find ourselves in one of these habitable universes. But the multiverse also raises new questions about expansion. If other universes are expanding at different rates, could they collide with ours? Could the expansion of one universe affect the expansion of another? Could there be regions of space-time where multiple universes overlap? Some theories suggest that the multiverse itself is expanding, creating space for new universes to form. This creates a hierarchy of expansions. Our universe expands within a larger multiverse, which might expand within an even larger structure. The process could continue forever, with expansions within expansions stretching to infinity. The multiverse hypothesis is currently untestable, but it illustrates how the expansion of space opens up possibilities that stretch our imaginations. If space itself can expand, then perhaps the very concept of universe is too small to contain the full scope of reality. These speculations point toward a future where expansion might lead to discoveries that revolutionize our understanding of existence itself. The accelerating expansion of space is already changing the fundamental structure of the universe in ways we're only beginning to understand. As expansion accelerates, the cosmic web of galaxies is being stretched and torn apart. Galaxy clusters that are barely held together by gravity today will be pulled apart by expansion in the future. The largest structures in the universe are already dissolving, leaving behind increasingly isolated island universes. This process is irreversible. Once expansion carries galaxies beyond each other's gravitational reach, they can never reunite. The universe is becoming more and more fragmented, with each galaxy group evolving in isolation. Future civilizations will see a much emptier sky than we do today. The acceleration is also affecting the flow of time itself. As space expands faster, the red shift of distant light becomes more extreme. Light from the most distant galaxies is already redshifted to radio wavelengths. Eventually, this light will be redshifted to wavelengths longer than the size of the observable universe itself, making it impossible to detect. This creates a kind of cosmic censorship. The expansion of space is gradually erasing the evidence of the Big Bang and cosmic evolution. Future observers will see a universe that appears static and empty, with no way to discover that it was once filled with galaxies and rich with structure. The expansion is also changing the nature of space itself. As dark energy becomes more dominant, the properties of space-time may evolve in ways we can't predict. The universe of the future might operate by different rules than the universe of today. These changes are happening slowly by human standards, but they're reshaping the entire cosmos on time scales that dwarf the existence of any civilization. The expansion of space might eventually become so extreme that it tears apart atoms themselves in a final cosmic catastrophe. If dark energy continues to accelerate expansion, we might be heading toward a scenario called the Big Rip. In this future, expansion becomes so rapid that it overpowers all other forces in the universe, including the forces that hold matter together. The universe would literally tear itself apart at the most fundamental level. The Big Rip would unfold in stages. First, galaxy clusters would be torn apart as expansion overpowers gravity. Then, individual galaxies would dissolve as expansion becomes stronger than the gravitational forces holding them together. Solar systems would be next, with planets ripped away from their stars. Eventually, expansion would become so extreme that it would overpower the electromagnetic forces holding atoms together. Molecules would be torn apart, then atoms themselves would be shredded as expansion pulls electrons away from nuclei. Even atomic nuclei would be ripped apart as expansion overpowers the strong nuclear force. The final moment would see expansion tearing apart space-time itself. The fabric of reality would be stretched beyond its breaking point, creating a universe where distance, time, and causality lose all meaning. The Big Rip would be the ultimate triumph of expansion over all other forces in the universe. This scenario is speculative and depends on the future behavior of dark energy, but it illustrates how the expansion of space could lead to consequences that are literally unthinkable. The gentle expansion we observe today might be the beginning of a process that will ultimately destroy everything we know about reality. The possibility of the Big Rip forces us to confront the most extreme implications of cosmic expansion. Even if expansion doesn't tear the universe apart, it will still lead to a future that is unimaginably different from today. The most likely scenario is that expansion will continue forever, but at a decreasing rate. The universe will grow exponentially larger and exponentially emptier, approaching a state called heat death. This is a universe where expansion has spread all energy and matter so thin that nothing interesting can ever happen again. In this future, the observable universe will shrink to include only our local group of galaxies. All other galaxies will have disappeared beyond the horizon, making the universe appear small and static to future observers. The cosmic microwave background will be redshifted to undetectable wavelengths, erasing the last evidence of the Big Bang. Stars will burn out one by one, leaving behind white dwarfs, neutron stars, and black holes. These remnants will orbit each other in ever-widening spirals as expansion carries them apart. Eventually, even these bound systems will be separated by the relentless growth of space. The final chapter will be written by black holes, which will slowly evaporate through Hawking radiation as they shrink. They'll release their energy back into the expanding universe, creating a brief flicker of activity in an otherwise dead cosmos. When the last black hole evaporates, the universe will be left with nothing but photons and elementary particles spreading through an ever-expanding space. This heat death scenario represents the ultimate victory of expansion over organization. The universe will become a place where entropy has reached its maximum, where no energy can be extracted to do work, and where the very concept of events becomes meaningless. But even this dismal future contains profound mysteries about the nature of existence. The expansion of space raises questions that might be fundamentally unanswerable, pushing the boundaries of human knowledge to their limits. We can measure expansion, predict its effects, and trace its history. But we can't explain why it happens or what it means. The expansion of space seems to be a basic feature of reality, like the existence of mass or the flow of time. We can describe it, but we can't explain why the universe chose to be this way instead of some other way. This limitation reveals something important about the nature of scientific knowledge. Science is incredibly powerful at describing how things work, but it struggles with questions of why things exist at all. The expansion of space is a perfect example of this limitation. We can map its effects with incredible precision, but we can't answer the deeper question of why space expands instead of remaining static. The expansion also forces us to confront the possibility that some questions might be literally unanswerable. If the universe is expanding into nothing, then asking what lies beyond it is meaningless. If the Big Bang was the beginning of time, then asking what came before it is impossible. These aren't just limitations of current knowledge. They might be fundamental limits on what can be known. Perhaps the most profound implication is that expansion makes the universe fundamentally mysterious. We live in a cosmos that is larger than we can observe, older than we can trace, and more complex than we can understand. The expansion of space has made the universe not just physically vast, but intellectually humbling. This humility might be expansion's greatest gift to human consciousness. The recognition that reality is far stranger and more wonderful than our everyday experience suggests. The expansion of space connects us to the deepest mysteries of existence, while simultaneously making us infinitely small within the cosmic story. Every atom in your body was once compressed into a region smaller than a proton during the Big Bang. The expansion of space has been stretching the universe for nearly 14 billion years, carrying those atoms through cosmic evolution until they became part of you. You are literally made of expanded space-time, shaped by the same forces that drive galaxies apart. This connection makes the expansion of space intensely personal. The growth of the universe isn't just an abstract physical process. It's the mechanism by which the raw materials of existence were transformed into the complexity we see today. Without expansion, there would be no galaxies, no stars, no planets, and no life. But expansion also reveals how vanishingly small we are in the cosmic scheme. The observable universe contains at least 2 trillion galaxies, each with billions of stars. The actual universe is probably much larger, possibly infinite. Expansion is constantly revealing new regions of space that dwarf everything we've ever known. This creates a profound tension between significance and insignificance. We are significant because we are part of the cosmic story, products of the same expansion that shapes the universe. But we are insignificant because expansion reveals a universe so vast that our entire observable region is just a tiny sample of a much larger reality. Perhaps this tension is itself meaningful. Maybe the expansion of space is the universe's way of creating both connection and perspective, showing us our place in the cosmic story while simultaneously revealing how much more there is to discover. The expansion of space makes us both everything and nothing connected to the cosmos and lost within it. The mystery of cosmic expansion will probably outlast our species, our planet, and our sun, continuing to puzzle minds we can't imagine. Long after Earth has been consumed by the expanding sun, long after our galaxy has merged with Andromeda, long after the last stars have burned out, the expansion of space will continue. It will be the most persistent feature of reality, outlasting every structure it helped create. Future forms of intelligence, if they exist, will still be trying to understand why space expands and what it means. These future thinkers will have advantages we can't imagine. They might have access to regions of space we can never observe. They might understand the nature of dark energy and the quantum structure of space-time. They might even develop technologies that allow them to manipulate expansions itself. But they'll also face limitations we can't foresee. Expansion will have carried most of the universe beyond their horizon, making it even more difficult to study the cosmos as a whole. The evidence for the Big Bang will have been redshifted into undetectable wavelengths. The universe will appear smaller and more mysterious than it does to us. This creates a kind of cosmic irony. The expansion that allows complexity and life to exist also ensures that the universe becomes increasingly difficult to understand. Each generation of observers will see less of the cosmos than the previous generation, making the mystery of expansion deeper rather than shallower. Perhaps this is appropriate. The expansion of space is the closest thing we have to a truly fundamental feature of reality. It deserves to remain mysterious, challenging every form of intelligence that emerges from the cosmic process it enables. The expansion of space will be asking questions long after we've stopped trying to answer them. Whether expansion continues forever or eventually reverses, it has already written the most important chapter in the story of everything. The expansion of space is what allowed the universe to evolve from a hot, dense state into the rich, complex cosmos we inhabit today. Without expansion, the universe would have remained a uniform plasma, too hot and dense for atoms to form. With too much expansion, the universe would have become too cold and sparse for stars and galaxies to condense. The expansion rate we observe is just right for complexity to emerge. This fine-tuning raises profound questions about the nature of reality. Why does the universe expand at exactly the rate needed for stars, planets, and life to exist? Is this a cosmic coincidence, or does it reveal something deeper about the nature of existence? Are we living in the one universe out of many possible universes that happen to have the right expansion rate? The expansion also raises questions about purpose and meaning. If the universe is expanding toward heat death or the Big Rip, then everything we create will ultimately be destroyed. Does this make our existence meaningless? Or does it make every moment more precious because it's temporary? Perhaps the most important lesson of cosmic expansion is that we exist during a brief window when the universe is interesting. We live at a time when stars are forming, when galaxies are visible, when the cosmic microwave background can still be detected. This is a special moment in cosmic history, and we are fortunate to be part of it. The expansion of space has created a universe that is both beautiful and terrifying, meaningful and absurd, comprehensible and mysterious. It has given us a cosmos worthy of our wonder and our fear. The expansion of space is the ultimate expression of the universe's creativity, constantly making room for new possibilities we can't imagine. Right now, as you finish reading about cosmic expansion, space is growing at a rate that would make your head spin. New regions of space-time are coming into existence. New possibilities are opening up, and new mysteries are being born. The universe is literally creating itself as it expands, writing the story of existence 1 cubic inch at a time. This ongoing creation is the most remarkable feature of expansion. It's not just that space gets bigger, it's that space becomes more capable of containing complexity, structure, and surprise. Every new region of space is a blank canvas for cosmic evolution to paint with stars, galaxies, and perhaps forms of intelligence we can't conceive. The expansion also represents the universe's commitment to exploration. Instead of remaining static and predictable, the cosmos has chosen to grow, to change, to become something more than it was. This isn't a passive process. It's an active choice by reality itself to embrace uncertainty and possibility. We are part of this creative process. Our existence is both a product of expansion and a participant in it. We are the universe's way of understanding itself, of asking questions about its own nature, of marveling at its own creativity. Through us, the expanding cosmos has developed the ability to contemplate its own expansion. This makes us incredibly privileged observers of cosmic evolution. We exist at a time when the universe is young enough to remember its origins, but old enough to have developed consciousness. We can see the cosmic microwave background, observe distant galaxies, and piece together the story of how expansion has shaped everything we know. The expansion of space has made us possible, and we have made the mystery of expansion meaningful. The expansion of space is the universe's greatest magic trick, making something infinitely large out of a point smaller than an atom. We've journeyed through the discovery that shattered our understanding of reality, explored the mind, bending truth that space itself is growing, and confronted the profound mystery of what it means for everything to expand into nothing. We've seen how expansion created the conditions for stars, galaxies, and consciousness to emerge, and how it continues to reshape the cosmos on time scales that dwarf human existence. The most profound insight from our exploration is that the question, what is the universe expanding into, reveals the limitations of human language and thought when confronted with the deepest mysteries of existence. We are creatures evolved to survive in a world of boundaries and containers, trying to understand a reality that transcends these concepts entirely. But this limitation is also a gift. The expansion of space forces us to stretch our minds just as it stretches the fabric of reality. It challenges us to think beyond our everyday experience, to embrace mystery as a fundamental feature of existence, and to find meaning in a universe that is far stranger and more wonderful than we ever imagined. As we look toward a future where expansion will carry distant galaxies beyond our horizon, we can take comfort in knowing that we exist during a remarkable moment in cosmic history. We are witnesses to the universe's greatest creative act, the ongoing expansion of space itself. In studying this expansion, we participate in the cosmos's attempt to understand itself. The expansion of space remains the ultimate frontier of human knowledge, a mystery that will continue to inspire wonder long after our species has joined the cosmic dance of expansion and transformation. What questions will the expanding universe pose to minds we can't imagine? Subscribe to continue exploring the mysteries that await us in the vast, growing cosmos.